Hi everyone, and welcome back. In the last few videos, we saw how to represent periodic signals as linear combinations of complex exponentials. In this video, we're going to extend these concepts to also apply to non-periodic signals. So let's first revisit the Fourier series representation for the continuous time periodic square wave that we've looked at in the past few videos. This square wave over one period can be expressed as x of t equals 1 for absolute value of t is less than t1, and 0 for t1 is less than absolute value of t is less than the period t over 2. And this square wave is periodic with period t. 2 videos ago, we calculated the Fourier series coefficient Cn for the square wave as Cn equals 2 times sine of n omega naught t1 over n omega naught t, where omega naught equals 2 pi over the fundamental period, capital T. And after calculating these Fourier series coefficients, we looked at the line spectra of these coefficients for a fixed value of T1 and several different values of T. Now what we're going to do here is we're going to interpret these Fourier series coefficients as samples of an envelope function. So the scaled Fourier series coefficients are T times Cn equals 2 sine of omega t1 over omega sampled at omega equals n omega naught. So we replaced n omega naught by a continuous variable omega, and then the scaled Fourier series coefficients are samples of this envelope function. So in a sense, by thinking about omega as a continuous variable, this function 2 sine of omega t1 over omega represents the envelope of t times Cn, and the scaled Fourier series coefficients themselves are simply equally spaced samples of this envelope. Let's look at another plot of the Fourier series coefficients for the periodic square wave, but this time as samples of the envelope t times Cn. So as you can see from these plots, as t increases, or as the angular frequency omega naught equals 2 pi over t decreases, the envelope, which is the same envelope in all three cases, is sampled with closer and closer spacing. And as t goes to infinity, the Fourier series coefficients approach the envelope function itself. Now, this was the basic idea behind Fourier's development of an equivalent of Fourier series for non-periodic signals, because we can think of a non-periodic signal sort of as the limit of a periodic signal as the period t goes to infinity. So here's a plot of the pulse train that we've been looking at for quite a bit now. This plot here shows a pulse train with t1 equals 1, and then the period t equals 4, t1 equals 4. So the square wave is 1 for half of its period and 0 for the other half period. Now I'm going to increase the period to t equals 8t1. Now t1 is still fixed this whole time, but now the duty cycle of the square wave is 25%. So it's 1 for a fourth of each period, and then 0 for the remaining 3/4 of the period. And I can increase it to t equals 16 times t1. Here's t equals 32 times t1. And if I look at, say, t equals 64 times t1, pretty much all we're left with is a single pulse centered at 0. So what we see is that if x of t is a signal of finite duration, which means that there exists a number t1 such that x of t equals 0 if absolute value of t is strictly greater than t1, then from this non-periodic signal, we can construct a periodic signal x tilde of t, where x of t is one period. So think about x of t as a single pulse, and then x tilde of t would be the entire pulse train. And then as the period t of x tilde of t goes to infinity, then x tilde of t is equal to x of t for any finite value of t. Now let's look at the effect of this on the Fourier series representation of x tilde of t. Now we kind of already saw this a few minutes ago, but I'm going to look at a plot of just the Fourier series coefficients themselves without the line spectra. So here's a plot of the scaled Fourier series coefficients t times Cn on the y-axis, and on the x-axis we have the angular frequency omega, which is n times omega naught. Now keep in mind that this is very different from the plot that we saw at the end of the third video, this plot here. We were plotting t times Cn versus the index n, and not the frequency omega equals n omega naught. So what we're looking at now is a plot of the scaled Fourier series coefficients t times Cn versus frequency omega equals n omega naught for different values of t. Here's the plot corresponding to t equals 4t1, which is a pulse train that's 1 for half of its period and 0 for the other half period. Here's t equals 8t1, t equals 16t1, t equals 64t1, t equals 128 times t1. And if I plot the scaled Fourier series coefficients for t equals 1024 times t1, pretty much the Fourier series coefficients have went from a discrete spectrum to a continuous function of omega, as we can see here. And this continuous function of omega is what we'll call the Fourier transform of x of t, as we'll see in a little bit. Now let's try to quantify this. I'm going to write expressions for the complex exponential Fourier series representation of x tilde of t, and then the Fourier series coefficient Cn. But keep in mind that x of t is a non-periodic signal of finite duration, and x tilde of t is simply a periodic signal where x of t is one period. So x tilde of t, using the Fourier series, is the sum from n equals minus infinity to infinity of Cn e to the power jn omega naught t, where the complex exponential Fourier series coefficients Cn are 1 over t times the integral from minus t over 2 to t over 2 of x tilde of t e to the power minus jn omega naught t dt. Now, since x tilde of t equals x of t for absolute value of t is less than the period t over 2, and also since x of t equals 0 outside this interval, we can rewrite the coefficient Cn as 1 over t times the integral from minus t over 2 to plus t over 2 of, instead of x tilde of t, simply x of t e to the minus j n omega naught t dt, which equals 1 over t times the integral from minus infinity to infinity of x of t e to the minus j n omega naught t dt. And so if we define the envelope x j omega of the scaled Fourier series coefficients t times Cn as x j omega equals the integral from minus infinity to infinity of x of t e to the power, instead of minus j n omega naught becomes a continuous variable omega. So x of t e to the power minus j omega t dt. Then the Fourier series coefficients themselves are given by Cn equals 1 over t times x of j n omega naught. And combining this expression for Cn with the original complex exponential representation of x tilde of t, we get x tilde of t equals the sum from n equals minus infinity to plus infinity of 1 over the period t, x of j n omega naught times e to the j n omega naught t, where 1 over t x j n omega naught are simply the Fourier series coefficients Cn. Now, since 2 pi over the period t equals omega naught, we can rewrite this as 1 over 2 pi times the summation from n equals minus infinity to plus infinity of x of j n omega naught e to the power j n omega naught t times omega naught. And as t goes to infinity, x tilde of t approaches x of t itself, and the right-hand side of this equation for x tilde of t becomes a representation of x of t. Also, as the period t goes to infinity, omega naught goes to 0, which means that this right-hand side here becomes an integral. And so using the fact that x tilde of t goes to x of t as t goes to infinity, we see that x of t equals 1 over 2 pi times the integral from minus infinity to infinity of x of j omega e to the power j omega t d omega, where x of j omega is defined to be the integral from minus infinity to plus infinity of x of t times e to the power minus j omega t dt. These two equations are known as the Fourier transform pair, and x to j omega is called the Fourier transform.